today we'll be diving deep into the heart of chemistry, and not just chemistry, including physics. Because when you hear quantum model and principle, when you hear about atom, you already know that it forms the basic of chemistry and that of physics. So in chemistry, you meet this thing at the beginning stage because we know that this thing forms the integral part or the forms a very, very important part in your chemistry learning. And then in physics, when you must have advanced to 003, that's before your 004, you get to meet this thing. When you talk about wave
Excuse me,
duality,
sir.
wave
Please.
duality of
You
matter.
are not audible.
What do you say, please?
Excuse me, sir. Please try to be audible. I can't hear you very well.
Who can hear me very well, please?
I can hear you very well,
So I
very
can hear you,
clear.
sir.
Like you're very lovely.
Okay. I said that when it comes to physics, we are not going to meet this thing in the beginning. Where you are going to meet them is in your 003. When you start to talk about wave duality of matter, how matter can behave as how light can behave as a wave and how light can behave as a particle. So the structure of atom and understanding how these atoms work is what will help us to fully understand how every other things work, how our body system work, how the medication we take work. Because it is after scientists discover this atom that we start building other things that we are seeing now. So you say this journey we are about to take now, or this journey we are about to pass through now, we start from a classical idea and then we move into the quantum world where we understand how electrons behave, how they can behave like waves. Then we also talk about how electrons are arranged in atoms, how light is emitted from atoms, and how these connect to all the beautiful things like all the firework you see and other things. So before we move into this, let's remember that scientists once saw atoms as indivisible particle. And when we are talking about the scientists, we are talking about atom. Then we move from that on seeing atoms as indivisible particles. So when scientists now start to work on these things, on this Dalton's atomic theory, so they work on this theory to know whether it is right or it is wrong. And then they discover that actually atoms have different parts. And these different parts makes up this atom. And you know that anything that have different parts can actually be divided. So these different parts is what we call subatomic particles of an atom. And then these subatomic subatomic particles, they are discovered by different people. We talk about Thomson, who discovered the electron, and how he proposed the plum-pudding model. Talk about the Rutherford-Goldford experiment, how he revealed a dense nucleus and empty space. So, but all these things, they were able to do something. They were able to do one thing, and that is to show us that atoms have subatomic particles. So I still remember that electrons were discovered first before others, and then we know the properties of this. But these theories are not able, or these models are not able to explain atomic stability, and that's what we are, and that's where we are starting from this night, from Bohr theory. So it could not explain why electron didn't fall into the nucleus, or why hydrogen emitted specific colors. And then Bohr theory came in and was able to do all these things. So this is John Dalton. The reason why we try to talk a bit about this guy is because of the work he did. He founded he's the founder of atom, or the person that discovered atom. So John Dalton is an English chemist, a physicist, and meteorologist, who is widely regarded as the founder of the modern atomic theory. His work, like I said, his work is portraying atom as a solid particle. And his theory proposed that all matter is composed of a tiny indivisible particle, known as atom, with each of them being unique, having unique properties and characters. Also remember him saying that all atoms of an element has the same properties, while different atoms of different elements have different properties. But as scientists work on this thing, they discover that the existence of isotopes shows that atoms of the same elements can actually have different properties. So back to what we are talking about this night, Bohr's atomic model. So Niels Bohr proposed a theory or a model that said quantized orbits. Okay, he proposed that quantized orbits. Niels Bohr proposed quantized orbits where electrons move without radiating energy. So he said that electron orbits the nucleus in specific specular path or energy level. What this guy is trying to say here is simple. He's trying to tell us that the planets are orbiting the sun, but it does that only in a fixed track. Let's bring it down. Imagine a stair, or what people call staircase. You can only stand on the first, or you can stand on the second step, or you cannot stand in between. So you can stand on first step or the second step, or you can't stand in between. So that's actually what this guy is trying to say here. So electron jumps from one level to another by either absorbing or releasing energy. So when electrons absorb or emit energy, they move to one level or the other. So now sometimes you may meet problem concerning this, like a calculation, and they will ask us to do they will ask us to calculate the energy released when an electron falls from n equals to 2 to n equals to 1 in a hydrogen atom. So first of all, we need to understand, or we need to know the formula for solving this problem. When we encounter any problem that has to do with energy level, if I have to find an energy release or absorbed by an electron, if you use the formula that says L equals to NH, L equals to NH, as you can see on the screen, equals to n bracket h over 2 pi. So the LDS stands for angular momentum. Hope you are jotting something down. Angular momentum. The n is the principal quantum number. As we go through this lesson, or we continue this lesson, you understand what principal quantum number is if you don't know it. So it can only exist from 1, 2, 3, 4, 5, and above. Then the h there is your Planck constant, which is equal to 6.626 exponential minus 34 joules. So to solve for this, you need to first understand that this formula we are seeing here, it helps us to understand how much energy an electron has when it's in a particular energy level. That is like if an electron is in this particular energy level, that's like it has this principal quantum number of either 1 or 2 or 3. This formula helps us to understand how much energy it has at that level. I don't know if anybody can hear me. Can you guys hear me?
Yes, sir. Yes, sir.
All right. From the example on our screen is not well structured actually. Say that for n1, n equals to 1, the energy is minus 13.6. For n equals to 2, the energy is minus 3.4. And then we are asked to calculate the energy release as from transition 2 to that of 1. And then they go ahead to give us the answer. But this example can be restructured very well, like to say calculate the energy release when an electron falls from n equals to 2 to n equals to 1 in a hydrogen atom. Because I forgot to tell you guys that Bohr's theory or Bohr's model works only for hydrogen atoms. So whatever question you are going to face there must be concerning hydrogen atoms. So when you are trying to solve this, you first of all solve them differently. You solve for n equals to 1. And how do you do that? You divide minus 13.6 by 1 square, like the number of the principal quantum number given to you, you square it, then you divide the energy by the answer you got by squaring that principal quantum number. So if the principal quantum number of the first n given to you is 1, 1 square is 1. So minus 13.6 divided by 1 is going to give you minus 13.6. And then the second one, you square the principal quantum number given to you. Square root of 2 is 4. And then you divide minus 13.6 by 4 to be given, because when you look at the calculation given to us, they say that the energy of the electron is minus 13.6. So now to find the energy at n equals to 1, we square the principal quantum number, which is 1 in the first phase. And then you divide it with that energy, you divide the energy of an electron by what you got. And the first one gave us minus 13.6. Then for the second one, that energy of an electron, which is minus 13.6, we divide it by what you got from the square root of the second principal quantum number, which is 4. When when you divide it, it's going to give us this minus 3.4. And then you do your simple calculation, which is to find the energy release. The energy release is the final energy minus the initial energy. The final energy we got here is minus 13.6, and the initial energy is minus 3.4. When you do your calculation, you are going to get this 10.2. Now, because the electron is falling minus 10.2, because the electron is falling to lower energy level, it loses energy. That's what it's trying to tell us here. Because the electron is falling to lower energy level, it loses energy. Now, why do we call the first one the final? I know someone will be confused. Why do we say that n equals to 1 is the final and n equals to 2 is the initial? Now, n equals to 1 is the final simply because when an electron moves toward the nucleus, it's dropping to a lower energy level. And as it moves far, it is increasing. So n equals to 1 is closer to the nucleus than n equals to 2, than n equals to 3. I don't know if anybody is confused. Is someone confused? Can anybody hear me? Can someone see my screen, please? Can anybody hear me, please?
Yes, sir. Yes, sir. I can see your screen. I can hear you, sir.
All right, let's move to atomic spectra, or what I normally call the fingerprint of element. So when electron falls to lower level, they emit energy as light. And each element gives unique color, just like a fingerprint. That's why we call it fingerprint of element, atomic spectra. So light emitted during transition. Light emitted during transition forms. Light emitted during transition forms spectral lines. And hydrogen emits when hydrogen element. It can emit red. It can emit violet light when it falls to lower level. What atomic spectra?
Please, can you repeat that fingerprint again? I did not get it.
Okay, I'm trying to explain the atomic spectra. So I said that the reason of describing atomic spectra as a fingerprint of elements, as a fingerprint, you know the essence of fingerprint, right? And you know the fact that two different people cannot have the same fingerprint. So that's the way this atomic spectra works. That when electron falls to lower level, they emit energy as light. And this energy they emit as light, it gives unique colors, just like a fingerprint that is different from what another one will emit when it falls to lower level. So if two electrons fall to lower levels, they're going to emit energy as light. And these elements are going to emit different unique colors, just like a fingerprint. And then I tell you that if you're talking about hydrogen, that hydrogen can emit red, it can emit blue, it can emit violet light. And also, this helps us to understand more when we are going to talk about the wave particle duality. So a formula for solving any problem that comes to you across this atomic structure is on our screen. We talk about the Bose model that explain line spectra, unlike previous model. And I forgot to say something. I forgot to say the limitations of Bohr model. When I was explaining Bohr's model or Bohr's theory, I said that it works for hydrogen alone. It only works for hydrogen-like atoms. You can't use it to do any calculation on chlorine or maybe on oxygen or something like that. So it works well for hydrogen-like atoms. Then it also cannot explain why electron doesn't spiral in. It doesn't explain multi-electron atom or fine structure. It doesn't account for sublevels or orbital shape of electrons. So you have this at the back of your mind anytime you are asked about the limitations of Bohr's model. It normally comes out during the exam. Same thing as how Dalton's atomic theory was restructured. So I'm talking about wave particle duality before I remember this. So they said that this is an idea that every particle or quantum object, like electron, proton, or even light, have. And sometimes they behave like a particle and also a wave, depending on how you observe it. They cannot behave like a particle and wave at the same time. They can either behave as a particle or as a wave. If you're talking about light, so that it can reflect, it can refract, it can diffract, and other things. And that's when it's behaving as a wave, because those are the characteristics of a wave. So sometimes electrons also do these things. Electrons also behave like both particles and waves. And then this thing can be solved using the Broglie theory or the Broglie wavelength theory. If you're asked to find the Broglie wavelength of an atom, that's what they normally used to ask. Then you can solve it using this formula on our screen. Wavelength equals to h over mv. I know that the parameters there, the wavelength, that's the formula for representing wavelength. Then the h there is Planck constant. And we know that Planck constant is 6.63 exponential minus 34. Also forget to say that wavelength should always be in meter. It's expressed in meter. Then the mass of the particle is represented by the m. That should be in kilograms. Then the velocity is represented in meter per second. So if you're asked to find the wavelength of an electron, and you are given a mass of 9.11 exponential minus 31. If you guys can see this thing on my screen, and then it's moving at a velocity of 2.2 exponential 6 meter per second. So you already know the formula for solving Broglie wavelength, which is wavelength equals to h over mass times velocity. So you input your figures there. The h stands for 6.63 exponential minus 34. Most times they give it to you during the question, or you see it in front of your question papers. Then the M is 9.11 exponential minus 31, and our velocity is 2.2 exponential 6. So when you do your calculation, you should be getting something like 3.31 exponential minus 10. And then the next thing we are going to talk about this night is Heisenberg uncertainty principle. So it's that we cannot know the position and the momentum of an electron at the same time. And they said that it's like trying to catch a moving fish in a more murky water. So electrons aren't in fixed paths, only probable region. They are not fixed. So we cannot find or we cannot know precisely the position and momentum of that electron. So this thing, they don't mostly come out during exam, actually. What you need to know is the formula mostly for physics, for solving these things, the formula for solving any calculation under Bohr's model or this the Broglie wavelength. But when it comes to chemistry, what chemistry will ask you is to maybe tell them the Newell's theory and its limitation, that atomic theory and its limitation, or maybe ask you to give the formula of the Broglie wavelength and what the parameter stands for. So the next thing we have here is Schrodinger's equation and wave function. This helps to describe electron as a wave and not as a particle. And the solution gives orbital. So this tells us the chance of finding an electron in a space. So what this guy is trying to say is that electrons behave as a wave and not as a particle. We treated electron as a wave, and he helped us to his solvings or the solution he gave to us help us to understand the region where electrons are most likely to be found. Okay, so just think like a rotating fan, blade. You can't see one exact blade, but a bro, and that's how an orbit works. So what you said help us to understand how orbitals are or how electron orbitals is. Then we move ahead to one of the most important things in chemistry, the quantum numbers. So talking about these quantum numbers, I would like to use the analogy given to us here, a hotel room. A hotel has a hotel room, and then in that hotel room, we have the floor, we have the room type, we have the room number, and then we have the occupants. So this is just how the quantum number works. Quantum number are a set of 4 numbers that describe the exact position, the energy, and the behavior of an electron in an atom. So this thing helps us to understand the exact position, the shape, the energy, the behavior, and even orientation, if that is not behavior, of an electron in an atom. So you may even address it as or say that this is an address of an electron, which has its energy level, and then the state that this electron lives, it's what we know as the sublevel. And the room is what we call the orbital. And how does it go? Does it go up or does it go down? That's what we call the spin direction. So the 4 quantum number is the principal quantum number, the angular quantum number, the magnetic quantum number, and then the spin quantum number. If you are not understanding anything, you can let me know, please. Let me know. So for the principal quantum number, it helps to tell us the main energy level. Like I said, it helps to tell us the main energy level or the shell of the electron. And this principal quantum number, it has a positive integers of 1, 2, 3, 4, 5 upwards. So it does not have any negative integer. It does not have 0. From 1, 2, 3, 4, 5, 6 upwards. But we normally make it of 1, 2, 3, 4 highest. So the higher the number, the principal quantum number, the more energy. And the more energy, the more larger orbitals. So more the principal quantum number increases, or more it goes, more energy it takes, and then more larger the orbitals goes. So if, for the example we have here, so that if you have principal quantum number of 3, if you have 3 sublevels, which is 3s, 3p, 3d. Remember, you have 4 quantum numbers. So this is just like the first one you need to know. And this first one just tells us only the main energy level that this thing exists. Does the energy level, is it existing in X, or is it existing in P or D or F? So now let's talk about the second quantum number, the angular quantum number. So the angular quantum number, you can call it the azimuthal quantum number. It tells us about the sublevel or shape of orbital. So this thing depends on the value or the angular quantum number. The possible value under it is from 0 to -1. And then, like I said, this is more like the shape, sublevel of an orbital or shape of an orbital. So for LO equals to 0, because it starts from 0 to -1. So for S, it's spherical. For P orbital, it's dumbbell. For D orbital, it's clover. For all these things, I don't think JUPEB will be asking you that. What JUPEB will normally ask you concerning this thing is know the meaning of angular quantum number, which is, it helps us to understand the sublevel or shape of orbital. And then they can ask you to state the values or the numbers under it, which is from 0 to -1. Then the next one is the magnetic quantum number. This helps to define the orientation of the orbital in 3D space. So it tells us the orientation of the orbital, or it defines orbital orientation. So the value of the magnetic quantum number is from -1 to +1. That's -1, 0, +1. And this is just 3. This exists for p orbitals. You know that when you are trying to fill in an atom, you have px, py, pz. And that's just what this magnetic quantum number is trying to say. And also, one thing you should have in mind is the magnetic quantum number is trying to tell us that each orbital can hold only 2 electrons. The px can only hold 2 electrons. The py can only hold 2 electrons. The pz can only hold 2 electrons. And then we talk about the last one, the spin quantum number, which describes the direction the electron is going, or the direction the electron is spinning. And the value under this is plus half or minus half. So two electrons in one orbital must have opposite spin. That is what this quantum number is saying. Whether it goes up or it goes down arrow. Just like saying that two people can share a room, but only if they sleep opposite each other. You cannot sleep the same direction. So why these quantum numbers are important? I don't know if it's here, but why these quantum numbers are important is it helps us to locate electron inside an atom, and not just locating this electron, to predict their chemical behavior, and also to understand bonding and atomic structure. So when you go into bonding, you see how this thing help us to understand this. So let's talk about the orbital shape. So we normally hear about XPDF. Okay. And orbital is a region around the nucleus. Know why this is not here. An orbital is a region around the nucleus where an electron is most likely to be found. Now, when we use the word most likely, it's trying to tell us that it doesn't mean the electron is locked in there. It's just that it has a high probability zone of being found there. So each orbital can hold just a maximum of 2 electrons. Then you have different orbitals here. The S orbital, the shape is spherical shape, like the ball shape. And then sub-level under this is 1 per energy level, starting from number 1, n equals to 1. So then it can, like we say, it can hold maximum of 2 electrons. Then for the p orbitals, each shape is dumbbell, or you can say this number 8. You know number 8, the shape of number 8. Yes, that is the shape of p orbital, because they might ask you to represent an electron using this shape or something like that. So this can be found in objective questions mostly. So it has 3 orientations: px, py, and pz. And then this p orbital, it starts from second energy level, n equals to 2. Start from, because when you are writing what I'm trying to say here is when you are writing an electronic configuration of any elements, you first of all write the s orbital. When the s orbital is filled up, which is your 2s1, 2s2, you move to the p orbital. And say that p orbital can hold maximum of 6 electrons. Maybe like 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. And then we talk about the next one, which is the d orbital. So d orbital, it has a compressed shape. And then it is found in 3rd energy level. And of course, it's found in 3rd energy level, and it has 5 orientation, and can hold maximum of 10 electrons. That means it has, something like when it comes to scandium, vanadium, titanium, iron, manganese, and all of them, use zinc, where we have 3D1, 3D2, 3D3, 3D4 till 3D10. So that's what the orbital is all about. Then for the last one, which is the f orbitals, you say that the f orbital is even more complex, and it starts from the 4th energy level. At your age, you have nothing to do with f orbitals. It has 7 orientation and can contain up to 14 electrons. Now, the final part of our class this evening is talking about the principle guiding this filling of electrons. So let's talk about the first one, the Hubbard's principle. It says that electrons fill the lowest energy orbital first before going to the higher one. So orbitals fill in, orbitals get filled in order of increasing energy. So when you're writing, it's trying to tell you how to write your electronic configuration. That you start from the lowest energy orbital first before you go to the higher one. 1s, 2s, 2p, 3s, and so on. So when giving something like an oxygen to write, you know that oxygen has an atomic number of 8. So you can start by filling the first orbital first, 1s2, 2s2, then 2p4. Now, the next one is the Hund's rule, the maximum multiplicity rule. We say that electrons are placed in orbital of same energy level, like in P, E, or F. That when electrons are placed in orbitals of same energy level, like in S, P, D, or F orbitals, they will first fill singly before pairing takes place. So just like a student that prefer to sit alone on the bus first. When you are going somewhere, people want to sit first on the bus. Then if the bus did not contain them, then they will now start lapping someone. That's just how electrons work. And that's what Hund's rule is trying to tell us, that this thing, they first of all fill in singly before you start to pair them. So if they fill in first and then there's still more, then you cannot start to pair. Why is this thing so? It's to reduce repulsion among electrons and to increase their stability. Just like in nitrogen, which have 1s2, 2s2, 2p3. Now our focus is on that 2p3. That 2p3, you can expand it into px, py, and pz. So they will first of all fill in singly. And then due to it is nitrogen, after the first one enter under px, the second one enter under py, the third one enter under pz. There will not be any electron remaining. But if it is something like maybe an oxygen, the fourth one will come and enter under px again to complete it. So that is what it's trying to tell us there, that electron, when placed in orbital of same energy level, remember it must be in same energy level, then they will fill in singly first before pairing begins to take place. Now, the next one is Pauli exclusion principle. This principle states that no two electrons in the same atom can have identical quantum number. So no two electrons in an atom can have all 4 quantum numbers the same. This 4 quantum number, which is the principal quantum number, the azimuthal quantum number, the magnetic quantum number, and the strain quantum number, they cannot have the same value for all the 4 quantum numbers. And then also know that an orbital can hold 2 electrons only, but they must be in an opposite direction. So they must differ at least in spinning. So even if they are the same in their principle, they are the same in azimuthal, they are the same in magnetic, they must at least differ in the way they spin. So before we close here, we are talking about you give a sample here. Phosphorus, which has electronic configuration of 1s2, 2s2, 2p6, 3s2, 3p3. You see that here, electron can only hold orbital can only hold 2 electrons at the same time in a particular direction. If this first electron is if the first electron is for 1s, what 1s can hold is only two electrons, which is 1s1 and 1s2. Then the 2s can only hold two electrons, which is second orbital, 2s1 and 2s2. The third orbital can only hold 6 because it's p. And when you expand it, you fill in singlet first, px1, py1, pz1, then you pair it, and then you move into the next one, which is your 3x. 3x can only contain 2 electrons, and you move into your 3p, which can only contain for phosphorus px1, py1, and pz1. So what we did today is that we talked about how atoms works, or the simple structures of atoms, the quantum models, and their principles. We talked about the principle like Hubbard's principle, Hooke's principle, Fourier exclusion principle. You should know this principle because they must show as far as chemistry is concerned. What you are saying here, even if you are giving example with any type of element or any element, even if it's oxygen, just write out the electronic configuration first, and then the remaining unfilled orbital, you expand it and can be able to show that this thing fill in singly before pairing can take place. We also talk about orbitals, the s orbital, p orbital, d orbital. At least move up to d orbitals, because I believe that your training or your understanding now stop at the static element. So the f orbitals, I don't think any question can come from there. We also talked about the quantum numbers, the principal quantum number. I'm trying to tell you that this thing is like the address of an electron. It's like an electron address. We say that the house the electron living is what we call the energy level. The state of that electron is the sublevel. The loom is the orbitals. And how do you even sleep? Do you lie down? Do you go up? Do you lie up, or do you lie down? So these are just simple things to help you to memorize, because JUPEB syllabus is very, very large. And then we also talk about some other theories under quantum models and atomic structures, like the Bohr's theory, and then that of atomic spectra, that of wave particle duality, which you get to know more when you do your physics, and then the uncertainty principle and the rest. So, did anybody have any question before we close for today?
No question, sir.
Okay. Thank you for coming to the class. You guys